background for introducing Luca. So Luca is a master's student at the Technical University of Munich and will be presenting work done during his ongoing master's at the Helmholtz Institute of Computational Biology in the TICE lab. Take it away.
Okay, I hope you can see my screen. Hey everyone, very excited to give this talk today on modeling single cell dynamics using unbalanced parameterized MonchMap. And yes, as already mentioned, this work was done during my master thesis at Helmholtz Munich in the TICE lab. I want to start by giving some preliminaries on optimal transport. So optimal transport in generally is concerned with how can we transport a source distribution into a target distribution with minimal cost. And currently, due to computational reasons, the most commonly used formulation here is entropy regularized optimal transport. Here one computes a probabilistic mapping, so one-to-many mapping, where one source point gets mapped to multiple target points with different weighting. On the other hand, MonchMaps compute a deterministic mapping, so a one-to-one mapping. And here recently, it has been proposed to learn MonchMaps through a parameterization by input convex neural networks using a minimax optimization. And having access to a parameterized model gives the additional advantage that now one can apply this to unseen data points and also map to points outside of the target, of the set of target points. And this is not possible for entropy regularized OT. Now, some of you might know Waddington OT, which uses entropy regularized OT to model single cell dynamics. In this work, we propose to instead use parameterized MonchMaps to do this. And now, why do we want to model single cell dynamics with optimal transport? Here, the goal is to model the change of a cell distribution over time. And if we assume that cells only move short distances over short time periods, then it is reasonable to model this relationship using optimal transport. And this was first proposed by Waddington OT, by Schiebinger et al. And here they compute mappings between two cell distributions. Now with parameterized MonchMaps, we have a few advantages. We can now additionally apply our learned model to unseen data points. And through the deterministic mapping, our model directly yields velocity vectors. Through this, we can create a full state space Waddington landscape. So we can evaluate our model on the whole cell landscape. However, there are also some challenges to parameterized MonchMap. One of them is that there exist multiple extensions of optimal transport, and these are not straightforwardly applicable to parameterized MonchMap. And one of them is unbalanced optimal transport. What is meant by unbalanced here? If you look at the synthetic data here on the right, you can see that mass is unevenly distributed. So in the bottom left and the top right, we have more mass than in the top left and the bottom right. And in the standard OT formulation, through conservation of mass, we need to cover the full target and source space. So here, balanced optimal transport would compute a diagonal mapping to fully cover the mass. And there exists an unbalanced formulation where we have an unbalanced parameter for source and target. We set this to the same for simplicity reasons. This is tau. And when you lower tau, you increase unbalancedness in the computed mapping. And you can see that by lowering tau, we end up with a sole vertical mapping here in unbalanced optimal transport. Now, as our main contribution, we extend parameterized MonchMaps to the unbalanced setting. And here our goal was to mimic the behavior of unbalanced OT, including the unbalanced parameter tau. And due to time constraints, I won't be able to go into all the technical details here. But in short, we do this by transforming distributions through a resampling step, which is based on batch-wise unbalanced OT. And we show that when we keep tau set to 1, we recover the standard parameterized Monge maps where we learn a diagonal mapping. And when we lower tau, like in unbalanced OT, we can gradually increase unbalancedness and end up at a vertical mapping. And this is also seen in the learned potential functions, which we have plotted at the bottom here. So you can see on the left, we have a vertical and a diagonal mapping, and on the right, we have a sole vertical mapping. Now, why is this all interesting for single cell data? Well, often in single cell data, we have asymmetric cell growth. This means that parts of our cell distribution grow faster than other parts. And one example is what we looked at, the pancreas data set. And here on the right, you can see it plotted as a UMAP, where we have partitioned it into 3 parts. And now, why is this a problem? Well, the right-hand side of the data set grows way faster, what we call NEB, than the top left part, EB. And now in the middle left, you can see this NGN3 part. Here we know from biological ground truth that this should be mapping up towards this EB part. However, since the NEB part grows so much faster, it has a lot more mass, and to effectively cover this mass in a balanced OT setting, this part would need to map back towards the NEB part. And so here we definitely need to incorporate some kind of unbalance. We introduced another way to do this by incorporating prior knowledge. This was already proposed in Waddington OT based on growth rates. Growth rates are computed using proliferation and apoptosis genes. And in Waddington OT, this was used for entropy regularized optimal transport. And here we adapt this to parameterized Monge map. In practice, we do this by having a weighted sampling on our input distribution based on the per cell computed growth rates. We evaluated our methods on the pancreas data set, and here we wanted to quantify performance based on biological ground truth. And herefore we used the cell ring pipeline. And we aggregated known cell type transitions here. So for example, we know that the cell type F plus alpha should be mapping to alpha, or that our NGN3 part of the data set should be mapping up towards the E part. And here we aggregated the percentage of correct cell type transitions as our main metric. And we compared our method to established trajectory inference methods, Waddington OT, SCVelo, and trajectory method. As 2 other metrics, we looked at cell type redundancy, where we computed predicted terminal states with cell rank based on the learned dynamics of each model. And you can see that only our 2 newly proposed methods managed to recover all the terminal states. Secondly, we looked at velocity consistency with the idea that cells close in gene expression space should also have a similar cell trajectory. And you can see that in general, PMM plus GR through the incorporation of prior knowledge performs best, while unbalanced parameterized Monge maps performs second best. Additionally, PMM shows promising results, but performs especially bad on the NGN3 part of the data set. And this is exactly due to the aforementioned reason. And we can also validate this visually. Here, we plot the velocity embedding streams of our different methods. And you can already see that for parameterized Monge maps, the standard formulation, we have this flow to the right of the NGN3 cells. By incorporating unbalancedness in unbalanced PMM, we can remove this right flow and now end up with something in between going to the left and to the right. And then by incorporating prior knowledge in PMM plus GR, we see that now we have this flow upwards to the EB branch. And when we take a look at SCVelo and TrajectoryNet, we can also validate our numerically results that SCVelo performs worse on the right part of the data set, and TrajectoryNet fails to recover correct cell type transitions on most of the data. For Waddington OT, since we can't get velocity vectors, there's no straightforward way to compute the velocity embedding stream. Now, I also want to show this potential function that's learned by the input convex neural network of our best performing method, PMM plus GR, because here there's we can interpret this as some kind of pseudo time. So we can see that pseudo time increases towards the terminal state on both the right-hand side and the left side, here branching on the left side. Summarizing, we applied parameterized Monge maps for modeling single cell dynamics and showed that it is a promising approach, but incorporating unbalancedness is crucial. We introduced unbalanced parameterized Monge maps, which is a new way of incorporating unbalancedness into the PMM formulation and PMM plus GR to incorporate unbalancedness with and without prior knowledge into parameterized Monge maps. We show that our methods outperform well-established trajectory inference methods in single-cell dynamics. Additionally, our methods naturally extend to other modalities, for example, site-seek or attack data. I want to thank my amazing co-authors at Helmholtz Munich, and our code will be released through Moscot, which is an optimal transport framework for single cell, which is getting developed at the PyStat. Lastly, I'm going to be at poster 43 at the upcoming poster session for potential more discussion and more details on the technical side. Thank you all so much for listening, and I'm looking forward to your questions.
Thank you so much, Luca. Do we have any questions? In general, please send your questions in the Q&A while the talk is happening. While the talk is happening so that we can streamline here. But if you're all still thinking about your questions, then I recommend going to visit Luca at his poster 43. And because we're kind of on a tight time frame, we might keep moving along. Thank you so much, Luca. Okay, next.